Hi, I'm Regina and this is my lab 2 on the magnetic field of a bar magnet. For this lab, here's a brief outline of what I will be discussing. The purpose of the lab is to measure the distance dependence of a magnetic field due to a bar magnet and compare those measurements to the appropriate equations / Biot-Savart law and build a computational model of the magnetic field. For this lab, the system is the magnetometer and the surroundings is the magnet bar. In this lab, I use the Biot-Savart law, which is used to calculate the magnetic field derivative, and the magnetic dipole moment, which is defined as the direction of a magnetic field is the same as the direction of the magnetic dipole moment. For the first part, I had to find the magnetometer on my phone. I measured on-axis magnetic fields by first putting my bar magnet on one end of the oriented meter stick east-west with its axis pointed along the meter stick. Then I placed my phone away from the magnet and perpendicular to the meter stick. Then I slid my phone across the meter stick, and when I found the absolute value of the x component at its max, I marked it and did the same process to find the absolute value of the y component at its minimum. Then I measured off-axis magnetic fields by using the same measure on axis magnetic fields but zeroing out the x component. But then I will find the distance from the net magnetic field that it has on 100 teslas. This distance is d-perpendicular, and from here I move the phone horizontally to put the sensor a distance d from the magnet. Here are a preview of my results. The initial conditions: the magnet was placed on a true east-west axis. There's my distance dependence and the magnetic dipole moment. And as for observations, when the magnetometer is far away from the magnet, it measures a near zero magnetic field in the x direction, and as it moved closer to the magnet, the measured x component of the magnetic field increased. Experiment details. For these measurements, I had to find the distance from the magnet to the sensor that had an x component to the magnetic field of 5 different values. I measured the x component and the distance from the magnetometer to the magnet. As you can see, I did 3 trials for each measurement to get an average that would be likely to reflect accurate results. You can see the averages in the bottom tables. This recorded data is useful for calculating the distance dependence, but plotting these values directly without using curve-fitting software is very difficult. But I'm able to plot the natural log of these values, which is shown on the right, which includes the equation of the line. By creating the graph, the experimental value of the distance dependence is simply the slope of my calculated line. So the value is negative 2.5712. Now that we have a value for n, we can use the equation of a magnetic dipole on the axis to determine the magnetic moment of the magnet. From our line equation, we can see that the y-intercept is equal to the natural log of the constant for the dipole equation. From k, we can use that to find mu, which I calculated to be 3.1834 amps meter squared. I did 3 trials of d-perpendicular to get an average of 0.194 meters. The Excel file also helped me calculate Earth's magnetic field and the final magnetic field. For my computational model through GlowScript, my code includes the function for the magnetic field, observation locations, and orange arrows representing the magnetic field on axes. My code also included cyan arrows representing magnetic field perpendicular to on axes and magnetic fields 45 degrees from axes. These are my results the model printed from the code. My theoretical off-axis field was 2.6 10 to the negative 5th Tesla, and my experimental off-axis was 2.3 times 10 to the negative 5th Tesla. These measurements are not far off, so I would say that the computed 45-degree angle agreed with my measured value. Some possible errors could have been human error when inputting data in the spreadsheet, either not in the right column or row, other magnets / electrical equipment nearby, or bumping my phone, leading my data to not be accurate. Now on to the what ifs part of the discussion. What if you hadn't oriented your experiment to compensate for magnetic north and instead laid out the meter stick at some intermediate angle with respect to Earth's magnetic field? Would the results have changed? Well, the magnetometer app readings would be incorrect, thus our n, mu, and k values would be less accurate. What if you redid the experiment using 2 identical magnets stuck together end to end? How would you expect your measurements to differ? Well, the direction of the magnetic field will remain the same, but the magnitude of the magnetic field should increase, making it stronger. Ultimately, I was able to use the Biot-Savart law and calculate the magnetic dipole moment due to a bar magnet. I was able to see how, as the magnetometer moved closer to the magnet, the x component of the magnetic field increased. And I was able to successfully create a computational model of the magnetic field and output a 45-degree angle that agrees with my measured experimental value. Thank you.